Now, multi-table joins. We already mentioned that multiple tables can be joined together. And with the join on syntax, now we will just write up front, table 1, join table 2 for whatever left, table 2, table 3, table 4. We will just write join table 2 on a condition. Usually it will be table 1, some column in table 1 equals to table 2. Then another join, table 3, on some column in table 3 equals to some column in other tables, right? Now, there are multiple ways of organizing a join. When you have multiple table joining, there's also always this consideration of who should be put into front, who should be put into join, and what's the joining order. This actually does not matter with to DBMS, because what DBMS does is it will create its own topology, and as long as you as a SQL writer can figure it out, DBMS will have no problem. But in order for people to understand properly, it's very important to write a proper join in the fixed matter, in a fixed approach, which generates some topology that is easy to understand. So the most common, two of the most common join topology, the first one is star join. So you will have one table in the center, and every table joins to that, every other table, all other tables join to this table, right? So as you can see, we have a table here. And the other two tables joins to this central table, which is shown here. Registration is joining with S, student S, where R student ID matches S student ID. Then registration again joins to course table, where the registration course ID equals to C course ID. Now, this is called star join because if you imagine, right now we only have two tables joining to the registration table. But if you imagine there are like 4 or 5 with one table in the middle, at the center, and all other tables surrounding that with a claw feet attaching to the middle one, the center one, then it looks like a star, right? This is why it's called star join. The other approach, this is a star join, where usually when you write the star join, usually you put the central table in the front clause and followed by one join for each leaf table in each join. Another join pattern is called chain join, where you will join from table A to table B, then from table B to table C. Now, for example, if I have an instructor and the course and the registration, I will join from registration to course with a R and C condition, then followed by join instructor, where C and I, course and the instructor, are joined on instructor name. So it will be like one table joining another. And this another table joins another, which forms a chain. Now, one thing to note is it's always easy to write from join clauses in the same order as the chain, but it's not necessary. You can write this join I, in front of this join course C, or you can even put the instructor here in the front. However, this will make reading difficult, not as easy at least. So it's recommended that you put the one table in the front and put all the chains, put all the other tables in the same order as the chain will go through. So it will be course first, joining registration, because course is the closest in this chain to registration, followed by the instructor. If there's another table after instructor, maybe instructor affiliation, then you will place the instructor affiliation table after instructor's join. And the one thing to note about chain join is you will try to avoid looping joins. Looping join usually means you have one table and there are two paths that you can join on. One is you can join to this table and join to this table, form one chain, or you can join from this table, another table to to the same table. Thus form a loop. Looping join usually comes when you have multiple source system. Each source system provides you with some kind of data. And this may cause data loss if there's any data inconsistency. If you have tuple A here and tuple B here, and this one are not overlapping, you have A but not B here, you have B but not A here, then when you join, it's very easy to mismatch the value. So try to avoid a looping join. If you have to some kind of this, it's better to perform a intersection, a union between these two middle tables, form one consolidated table and form one single chain. Don't do looping join. So if you combine star schema and the star join and the chain join together, you will have what we call a snowflake join, where in the middle, there's this central table. And you have four tables, each joining to the middle one. Now you can see why it's called the star join, right? 1, 2, 3, 4, this forms a star. And outside this star, there are more joining happening and each forming a separate chain. Or here, there's another smaller, for this dimension table, there's another smaller star join, right? So you will have one star join and whatever only leaves of that star join will have their own chain join or star join, and so on and so forth. This will come up with this will look like a snowflake. So it's called snowflake schema. And the most common usage of data warehouse query is this snowflake schema. We will talk about this when we talk about data warehouse. Now, after going through all the star join and the chain join and snowflake join, I know you will be thinking, why are we doing normalization? Didn't we take all the pain to normalize the large table and break them up? Why do we need to, now that we need to join, why do we do the normalization in the first place? So the answer is there are two types of data usage. One is called transactional, which is the operation side where you perform like purchase, online order, or credit card transactions, making phone calls. All this operational processing requires fast response and requires single entry, requires data integrity. They requires data integrity built into their system. So these kind of operations requires normalization to avoid complexity and redundancy and to improve performance, because in a normalized schema, usually your performance is faster because your tables are smaller and thinner. It has less columns, and because it has less columns, it usually has less rows, right? So normalized schema usually performs faster and it's simple in one or two in a separated scenario. However, there's another types of data usage, which is analytical. It will perform against the historical value, which also involves a variety of information from all aspects. When you perform analytical tasks, you will need to put all the information from all different areas together to form a some kind of research data set, which of course, the more data it contains, the better it is. So in this case, you will need to join from multiple places to perform complex transformation and calculation. This is when you need a join. Now, if this join is so painful, there is this way of a denormalization. Remember, we said denormalization for analytics is currently a common practice now to build another analytics database outside of a normalized database, operational database, to create an analytics denormalized analytics database where you will need to do less join. All right. So that's why we have a join and normalization. Each have a different way of usage, and the sum of the schema may not always be normalized.